What if I told you that the most important thing about 3I Atlas is not that it came from another star system, not that it crossed the orbit of Mars, not even that it is only the third confirmed interstellar object humanity has ever seen, but that after passing behind the sun, after disappearing into the one region of the sky where Earth-based telescopes lose control of the story, it came back behaving differently, slightly different in orbit, dramatically different in brightness, chemically richer than before, and active in ways that are still being argued over by astronomers who agree on the measurements, but not yet on the full meaning of those measurements. Because this is the part most headlines miss. 3I Atlas did not simply survive perihelion. It returned with new motion, new outgassing, new geometry, and new questions. And if you think slightly different means unimportant, remember what astronomers are actually measuring. When 3I Atlas was discovered on July 1st, 2025, by the NASA-funded Atlas survey in Rio Hurtado, Chile, it was already moving at about 137,000 miles per hour, or 221,000 kilometers per hour. At perihelion, as the sun pulled on it, its speed climbed to around 153,000 miles per hour, or 246,000 kilometers per hour. At those velocities, even a small non-gravitational push is not a trivial footnote. A tiny acceleration, if sustained long enough, becomes a measurable shift in ephemeris, and once the ephemeris changes, the story changes with it. NASA's official public position is careful. The agency says the comet's perturbations are small and compatible with outgassing, the familiar process in which solar heating turns subsurface ice into gas, and the escaping gas acts like microscopic thrusters. That is the conservative explanation. It is also the scientifically responsible one. But here is where things stop being simple. The object did not merely continue on a clean, unremarkable outbound path. Post-perihelion observations showed a statistically significant non-gravitational acceleration. Independent reporting on the updated JPL solutions pointed to a slight course change, significant brightening, and the possibility that the object shed a meaningful fraction of its mass during and after its closest passage to the sun. So the real question is not whether there is an explanation. The real question is whether the explanation we have is complete. And right now, it is not. Because if standard cometary outgassing fully solved the case, the story would already be over. It is not over, not even close. After perihelion, NASA's SphereX mission reported a dramatic increase in brightness 2 months after the object had passed closest to the sun. That timing matters. Peak heating does not always mean peak activity. Heat has to travel downward through the crust. Buried volatiles warm late. Pressure builds late, venting can erupt late, and SphereX did not just see brightness. It detected infrared signatures from water, carbon dioxide, organic molecules, methane, methanol, cyanide, soot, and rocky dust. The chemical fingerprints of a body that was still changing after many observers assumed the most interesting phase had already passed. That alone would be enough to keep astronomers locked in. But then the geometry becomes stranger. One of the most discussed features of 3I Atlas has been the direction of its dust structure. In a typical comet, dust gets pushed away from the sun by radiation pressure. Here, researchers highlighted a tail-like structure pointing sunward, the opposite of what a casual observer expects. The leading interpretation is not exotic propulsion. It is large, heavy dust grains, possibly hundreds of microns across, leaving the heated sun-facing side so slowly that solar radiation pressure cannot immediately sweep them into the familiar anti-solar pattern. That explanation is physically plausible, but it creates a new problem. If the dust is that coarse and the emission is that slow, then the coma and tail morphology are telling us the surface layers, vent locations, and particle size distribution of this object may differ in important ways from the comet behavior we are used to seeing at home. And this is where the script most people are telling you splits into two different realities. In the first reality, 3I Atlas is simply a weird but natural comet, one formed around another star, processed by interstellar space for eons, now reacting to solar heating in ways that look unfamiliar only because our sample size is embarrassingly small. In the second reality, every new oddity gets inflated into something artificial. I am not going to do that. But I am going to say something far more useful. We do not need to jump to science fiction for this object to remain deeply unsettling. A completely natural interstellar comet can still expose holes in our models, force revisions to our assumptions, and reveal how little experience we have with bodies that did not form in the solar system. Natural does not mean simple. Natural does not mean understood. And the observational record itself is already extraordinary. In early October 2025, when 3I Atlas made its closest pass to Mars, NASA's Mars Reconnaissance Orbiter, MAVEN, and even the Perseverance rover captured it from vantage points Earth could never provide. MRO viewed the comet from about 30 million kilometers away. MAVEN used ultraviolet observations to constrain its chemical output, including hydrogen and hydroxyl in the coma. Perseverance, fixed on the Martian surface, caught the object as a faint smudge in an exceptionally long exposure. These were not decorative images, they were leverage points. They gave scientists a different angle on the object at a moment when geometry mattered. Then ESA did something even more important. Using data from the ExoMars Trace Gas Orbiter orbiting Mars, combined with Earth-based observations, astronomers refined the predicted path of 3I Atlas by a factor of 10. Think about what that means. This was not just a prettier picture, it was a deeper lock on where the object was and where it was going. ESA described the result as the first time astrometric measurements from a spacecraft orbiting another planet had been officially accepted into the Minor Planet Center database. That is not a routine footnote. It is a rehearsal for the future. A demonstration that if a fast object enters the solar system and Earth loses sight of it near the sun, we may one day need off-world observatories to reconstruct the story before it is too late. But if ESA improved the trajectory so dramatically, why are we still talking about uncertainty? Because there are two different kinds of uncertainty. There is positional uncertainty, where exactly the object is, and there is physical uncertainty, what exactly the object is doing. The first can be squeezed down with more observations and better geometry. The second is harder, much harder. The object can brighten unexpectedly. It can vent asymmetrically. It can rotate. It can expose fresh volatile pockets. It can crust over, then rupture. It can throw off large grains and chunks that respond differently to sunlight than micron-sized dust. In other words, you can know where the comet is while still arguing about what mechanism is nudging it. ESA NASA Sphere blog, The Planetary Society. And after the object re-emerged from behind the sun, that distinction became impossible to ignore. Public reporting on the post-perihelion JPL solutions described a radial acceleration away from the sun and an additional transverse component, a sideways push, not just a straight recoil. That matters because a sideways component tells you something about geometry. Jets are not firing symmetrically. The surface is not venting evenly. Rotation, active regions, seasonal illumination, and internal structure all begin to matter. One of the peer-reviewed lines of work now argues that ordinary CO-driven outgassing can account for the measured acceleration over a plausible range of nucleus sizes and active area fractions. That is a serious result. It pushes back against sensationalism. But even that result does not erase the mystery. It relocates it. If CO-driven activity is enough, then where are the active regions? How are they distributed? How delayed is the heat transport? And how much mass has already been lost? Now pause there, because this is the open loop almost nobody is emphasizing. If the acceleration is natural, the object becomes more interesting, not less. A natural explanation still implies a nucleus capable of maintaining meaningful anisotropic activity after a solar encounter, while carrying a chemistry that appears rich in carbon-bearing compounds and a dust environment dominated by unusually large grains. That combination is not something we can wave away with the word comet and move on. Comet is a category. It is not an answer. And then there is the mass loss question, which may prove to be the most important clue of all. Reporting tied to the latest observations suggested that if the measured non-gravitational acceleration is interpreted through straightforward recoil physics, 3I Atlas may have lost on the order of more than 13% of its mass near perihelion, depending on the gas ejection speed assumed. That is enormous. Not impossible for a comet, not unprecedented in principle, but enormous, because mass loss is not merely a bookkeeping problem. Mass loss changes the nucleus. It changes torque. It changes rotation. It changes surface integrity. It changes where sunlight penetrates next. And once that feedback cycle starts, yesterday's comet is not the same as today's comet. Which leads to the next question. If 3I Atlas changed direction again, was it because it was pushed by one dominant outburst or because it is still evolving in stages? That is not a trivial distinction. A single event suggests a discrete rupture or venting episode. A staged evolution suggests a layered body in which heat is still unlocking buried reservoirs one after another. And if it is staged, then what we have seen so far may not be the final behavior. That is why the March 2026 timeframe matters so much. The object is now now on its way past Jupiter. NASA's public material has consistently described that encounter as part of its outbound journey from the solar system, not a capture event, not a braking maneuver, and not a threat to Earth. But if the nucleus is still physically changing while the outbound geometry continues to evolve, then the next observations are not just about position. They are about whether activity is fading, stabilizing, or preparing one more surprise. NASA science, NASA science. And here is where the object becomes a retention machine for astronomers themselves. They cannot let it go because each new dataset opens a different kind of mystery. Hubble constrained the nucleus size and revealed a teardrop-like dust structure. JWST captured near-infrared spectra. Sphere-X saw the coma in 102 colors and detected molecules that tell us about chemistry beneath the surface. MAVEN measured ultraviolet signatures at Mars. TESS re-observed the comet in January 2026 to probe activity and rotation. Different instruments, different wavelengths, different geometries, different times. And instead of collapsing the story into one neat conclusion, the combined dataset makes the object look more layered. That TESS dataset, by the way, is one of the quiet clues people are underestimating. NASA stated that TESS observed 3I Atlas from January 15th through January 22, 2026 during a special run to study the comet's activity and rotation. Rotation is the word to watch, because rotation is where a lot of unresolved stories converge. If an active comet is venting unevenly, those vents can torque the nucleus. Torque can change spin. Spin can alter sunlight exposure. Altered exposure can trigger new active zones. New active zones can shift the non-gravitational acceleration again. So if you want to know whether the latest directional changes are a settled story or the beginning of a more complicated one, the rotation solution may end up being one of the deciding pieces. There is another reason this matters. 3I Atlas is not just a comet, it is a sample from somewhere else. NASA emphasizes that objects like this are scientifically precious because they preserve clues about planetary formation in other star systems. But the moment you accept that framing, every unexplained feature becomes larger than this one object. If its crust chemistry, volatile layering, or grain size distribution differ materially from solar system comets, then 3I Atlas is not only telling us about itself, it is offering a distorted but invaluable message about the disk environment in which it formed. Perhaps around a star older than the Sun, perhaps in a region of the galaxy that no longer resembles its original birthplace, perhaps after drifting for millions or billions of years through interstellar space. And that creates a deeper cliffhanger hiding underneath the trajectory question. People keep asking, why did it change direction? The bigger question may be, what kind of body changes direction like this under solar heating? Not whether the physics is impossible, whether the object's internal architecture makes those physics inevitable. If you brought 1 billion different cometary bodies in from interstellar space, how many would behave like this? 1, 10, half? We do not know. We have only 3 interstellar detections in history, and only one of them, this one, has been observed with a global, multi-mission interplanetary campaign spanning Earth orbit, Mars orbit, the Martian surface, infrared all-sky surveys, space telescopes, and planetary defense infrastructure. Think about the choreography required just to keep this object in view. During one critical stretch, Earth-based instruments could not observe it because it was on the far side of the Sun. That forced scientists to lean on Mars assets, solar missions, and later returning observations after the object reappeared. Scientific American described the entire effort as an interplanetary race to study 3I Atlas before the opportunity vanished. That language is not hype, it is logistics. A fast-moving interstellar object does not wait for grant cycles, telescope committees, or convenient weather. If you miss the window, you miss the window, which means the data gaps around perihelion do not just create suspense for YouTube, they create real scientific blind spots. Scientific American and blind spots are where narratives diverge. On one side, you get sober astrophysics, delayed venting, evolving active areas, coarse dust, CO-driven recoil, mass loss, and improved trajectory fits. On the other side, you get the claim that because we do not have the whole answer yet, there must be no answer at all. That is not how science works. But here is the uncomfortable truth. For retention, uncertainty is more powerful than certainty, and 3I Atlas has delivered uncertainty at almost every level that matters. Brightness evolution, tail geometry, mass loss fraction, active chemistry, rotation state, and the exact partition between radial and transverse acceleration. That is why this object keeps pulling attention back even after the words, "It's just a comet," have already been spoken. And remember something else that is easy to miss. NASA has already said 3I Atlas poses no danger to Earth. Its closest approach to our planet was about 1.8 astronomical units, around 270 million kilometers, in December 2025. That should remove one temptation immediately, turning every unexplained behavior into an impact scenario. This is not that. The stakes here are not collision. The stakes are comprehension. Because if a body this small can still force a multinational, multi-orbit, multi-wavelength scramble simply to understand its post-perihelion evolution, then we have learned something humbling about our readiness for the next interstellar arrival. That is why ESA treated the Mars-based triangulation as a planetary defense rehearsal, even though 3I Atlas itself was never dangerous. Their point was not that this comet threatened us. Their point was that one day, a fast object might emerge from a difficult solar geometry, and the ability to use spacecraft around other planets to sharpen its ephemeris could become decisive. So 3I Atlas may end up being remembered not only as the third interstellar object, but as the case that taught us how blind we are near the sun, and how badly we need a distributed observing network if we want to understand fast movers before they are gone. Now let's come back to the phrase everyone is reacting to. Change direction again. If you hear that and imagine a sharp turn, you are already in the wrong movie. That is not what the best data say. The motion is subtle, the acceleration is small, the physics can be commentary, but subtle does not mean meaningless. In orbital mechanics, a small deviation from pure gravity is the signature of a process at work. A process means a source means structure, and structure is the real story. What kind of crust delays heating this long? What volatile inventory survives interstellar transit and then erupts this way near the sun? What distribution of jets produces the observed combination of brightening and non-gravitational terms? And is the object calming down, or simply between episodes? Because there is one more open loop here, and it may be the most dangerous one for anyone trying to make this story feel settled. The models that explain the current acceleration do so across ranges. Ranges of nucleus size, ranges of active area fraction, ranges of volatile dominance, ranges of thermal assumptions. That is normal science. But ranges are where future surprises live. If the nucleus is closer to the small end, the recoil picture changes. If active areas migrate, the transverse component can evolve. If rotation is faster or more chaotic than expected, a future burst can arrive from a geometry no one is currently favoring. The object does not have to violate physics to violate our confidence. And then there is Jupiter. Not because Jupiter is going to capture the comet. NASA's public tracking still frames 3I Atlas as outbound on a hyperbolic path that will ultimately carry it back into interstellar space. But because Jupiter is the next psychological checkpoint, March 2026 is where the audience expects finality. Either the object fades into statistical normalcy, or one more anomaly appears on the way out. One more brightness change, one more refinement in the non-gravitational solution, one more twist in the dust morphology, one more clue from spacecraft farther out. That is how this story sustains itself. Every time you think the object is leaving, it leaves behind a new question first. So let's state the evidence cleanly. 3I Atlas was discovered by a NASA-funded survey on July 1, 2025, as only the third known interstellar object. It traveled on a hyperbolic trajectory at extreme speed, passed near Mars, went behind the sun, and re-emerged with post-perihelion behavior that included significant brightening and measurable non-gravitational acceleration. NASA's Sphere-X observations revealed delayed venting and a chemically rich coma containing water, carbon dioxide, and organics. Mars assets and ESA's ExoMars orbiter improved the path solution with off-Earth geometry by a factor of 10. Researchers highlighted unusual dust morphology, large grain behavior, and open questions about the object's active structure. TESS re-observed it in January to constrain activity and rotation, and the strongest current modeling says the acceleration can be natural, likely driven by volatile outgassing. But natural does not mean fully solved, and that is the point. The strongest version of this story is not that NASA has no explanation in the absolute sense. It is more precise than that, and more interesting than that. NASA and the broader community have a working explanation for the broad class of behavior, cometary outgassing. What they do not yet have is closure. not on the complete internal architecture of the nucleus, not on the exact vent geometry behind the transverse acceleration, not on the full mass loss history through perihelion, not on the final rotation solution, not on whether the most dramatic phase of activity is over, not on whether the present model parameters will hold without revision as the object continues outward. So if you want the honest headline, here it is. 3I Atlas changed direction again, not by some impossible cinematic lurch, but by the kind of subtle, measurable deviation that tells astronomers the nucleus is active, asymmetric, and still giving up secrets. NASA has an explanation for the category. It does not yet have the full answer for the object, and until the chemistry, rotation, and recoil geometry lock into one coherent model, 3I Atlas remains exactly what a rare interstellar visitor should be, not a solved case, but an open file. And the final twist is this: the object is leaving, but the consequences are staying. Because long after 3I Atlas has faded beyond our instruments, the data it forced us to collect will keep working on us. It will shape the design of future planetary defense systems. It will influence how we model activity in interstellar comets. It will sharpen the case for solar blind spot missions. It will remind astronomers that the next visitor may not announce itself under convenient geometry. And if one small interstellar comet can do all of that simply by brightening late, venting unevenly, and nudging its own trajectory by a scientifically modest but symbolically enormous amount, then the real message of 3I Atlas is not that the universe sent us a threat. It is that the universe sent us a warning about how much of it we still do not know how to read. And if one more update lands, one more change in the non-gravitational fit, one more strange asymmetry in the dust, one more clue from the outbound data near Jupiter, then this entire story changes again. Not because the comet is defying physics, but because we are still catching up to the physics it chose to reveal. And that means the most dangerous assumption you can make about 3I Atlas right now is that we have already seen the final version of it. We probably have not.